So again, I tend to go on, and a good strategy is to play this at 2 times the speed until you get to the question you're interested in. But this 1.3 covers parent functions, and I'm going to put this in an attachment. On here on Desmos, I've done the most popular parent functions from the line to the parabola. I'll just turn off the dots there. Parabola, the cubic, the quartic, which probably have to zoom out to see, but see if I can get it like that. Yeah, you can't quite see the quartic very well. The absolute value graph, etc., etc., etc. And a good strategy, especially for learning how to graph these, is learn their domain and range. I'll just turn off that one. Here's the line, domain and range, goes on forever, XER, YER, and learn some common points. So 2, 2, 4, 4, and I'm just going to zoom in a bit. There we go. So you get 1, 1. And once you know these common points, like 3 of them, 4 of them, goes through origin, you'll be able to transform them no matter what. So a good one for the parabola is 0, 0, 1, 1, and then 2, 4, right there, somewhere around there, and minus 1, 1, and minus 2, 4. And again, once you know these, you'll be able to transform them. So as you learn, and of course the domain of this goes on forever, but the range is limited by the vertex, depending on whether it's facing up or facing down. And so you should learn and fiddle with these to learn some basics about the transformations. For instance, the quartic always starts in quadrant 3 and ends in quadrant 1 unless it has a reflection on the x-axis, and then it starts in quadrant 2 and ends in quadrant 4. And people might say, well, how do you know where it starts and ends? You always read graphs along the x-axis from left to right. So wherever the graph first appears, in this case it first appears up here, and as I go to the right, it goes down to here. So graphs are always read from left to right along the x-axis because the x-axis is the independent variable, and it ticks on forever. If you think of time, time always moves from left to right or from beginning to end. It doesn't move backwards. And then you just want to learn, so for instance, quartics are very much like anything with an even power. They all begin in quadrant 2 and end in quadrant 1. So you want to learn the basics, and anything to an odd power always begins in quadrant 3 and ends in quadrant 1. These tools and how many bends are in them and how many turning points, these are good things to learn. Not only will it allow you to transform it, but it'll allow you to recognize a graph very quickly. An absolute value graph is very much like a parabola. Its range is dictated by its vertex. The square root function is limited both in range and domain. Both are equal to 0 and above. The rational function has 2 asymptotes, that y is equal to 0 and x is equal to 0, and you're going to learn a lot about this function. They're going to do a lot of rational functions, so it's good to get comfortable with the basic. And then you're going to learn what happens when, let's say, one is a square at the top and one's an x up top. Or actually, let's try a different one. Let's put x plus 1 at top and x plus 3 squared at the bottom. And you're going to learn that there's various shapes that happen. I'm trying to produce one that has 5. Let's see if I can produce one that has a couple of asymptotes. So we'll just do it like this. X plus 2 and x minus 4. And we'll just have that. And there, you can see this one has a whole bunch of vertical asymptotes. And you have to learn where you find your vertical asymptotes. They're always going to be at the restrictions at the denominator. So the vertical asymptotes will be when x is 4, when x is minus 2, and when x is minus 3, because that'll create a 0 condition in any of these brackets, which is impossible. You can't have a 0 at the bottom. And that's what creates those vertical asymptotes. And the horizontal asymptotes you're going to learn are dependent on what the power is up top versus what the power is at the bottom. For instance, at the power at the bottom here is going to be an x cubed. And you learn that because when you multiply these first ones out, you get an x cubed and an x to the 1. But if I have an x cubed up here, you're going to learn that the horizontal asymptote varies depending on what the ratio number is up front. And you'll get more into that. But what affects these things, it's good to learn. As well, you're going to learn all about different kinds of horizontal asymptotes, and even something called a diagonal asymptote. It has a different name. But anyway, it all starts with 1 over x, so you should learn about its domain and range. 1 over x squared is kind of unique in that y's values are always positive. And then this is a very important curve. You're going to get into it quite a bit, and it has a big role in biology. Growth curves, bacteria grows like this, viruses grow like this, finances grow like this. And so you can see it has a role in finances as well. And this is a decay curve. So radiation decays like this. There's several other examples that I can't think of right now. And then you want to learn your basics of your sine curve and what limits its range. Cosine curve has very similar range limitations. And then the tan curve is unusual. So you want to learn where its vertical asymptotes occur. And that all comes from the unit circle. And then in calculus, you're going to get more into the log curve. A log curve is directly related to a base 10 growth curve. And you'll discover that it's the inverse of it. So where 0, 1 is one number, 1, 1 is another. And up here you're going to have 1, 10, which means you're going to have a 10, 1 over here. So log curve is an inverse of a 10 base growth curve. And you'll get more into logs later. They always look complicated, but they're not really. And then the log curve just relates to the natural letter E. It's the inverse of an e to the power of x, and you'll get more into e in calculus. It's the inverse of an e to the power of x. E is a specific constant. I forget the value of e, but you'll get more into it as you go. 2.718. E is a fascinating number, and it's as much of a puzzle to mathematicians as pi is. And then you get to the reciprocal, which is cosecant, secant, and cotangent. That's the reciprocal of sine, cosine, and tangent. You get more into those, and they all have vertical asymptotes because they're reciprocals. Except for, the cotangent curve will look very much like the tangent curve. And then there's that e to the power of x. But just learning the basics of them will really help you, and learning what happens when you put a minus in front. And if the minus is outside of the x, so I'll turn this one on, versus when the minus is inside with the x in a bracket. You're going to discover you're not going to even notice a change, and that's because that minus gets squared. However, if there was a slight translation, you will notice the minus. Let's see if it will. Actually, I guess you won't. I think you'll notice it here. You will notice the minus here. And if I put it here and change the sign, you'll notice it, which is the same thing as putting it in front. And so you'll learn when it gets reflected in the y-axis versus when it gets reflected in the x-axis. And you'll learn that the y transformations are the easiest things to understand. It goes up 4, goes down 4. On to the textbook. Anyway, use Desmos. It'll speed up your learning curve. So 1.3 is just about understanding intervals of increase. So what is an interval of increase? Well, notice that this thing is coming down, and slowing down. And then suddenly it hits the vertex, and then starts going up and increasing dramatically to the power of 2. This, from the origin onwards, is an interval of increase. And this is an interval of decrease. Now, it seems obvious, but this interval decreases very steep here and then starts to shallow out here, very much like a ski hill. So if I were to inverse this, let's just inverse it, and just let's make it normal. And let's raise it by 5 just to see it. The interval of increase is now on the left until it reaches here and then goes down on the right. But you're also going to learn something happens. Let's say if this is a cubic, and I'm going to have to let's see if I can make it. Yeah, I'm going to have to do it like this. Plus 3 to try to make a more visible. And then x minus 4, let's say. I'm just trying to make it more visible. And put them closer together. There we go. Now you'll notice that this cubic has an interval of decrease here, then an interval of increase here, and then an interval of decrease here. Well, that means at some point, in order for it to turn around, there has to be a point where it gets less steep. And you're going to learn that in calculus. But at this stage, we're just learning what intervals of decrease are, intervals of increase, and intervals of decrease. So that's going to be something you need to spot. Then you're going to have to learn what an odd function is and an even function. An odd function reflects diagonally through 2 quadrants, and an even function reflects through the y-axis. I'll give you an example of an even function. And actually, I'm going to go to a totally new one here. So here's a good example of an odd function. The right side is reflected through origin into quadrant 3. Here's another good example of an odd function. The right side is indeed perfectly reflected. For instance, I'll find the exact opposite point here at minus 1, 1, as I would here at 1, 1. And I'll find another point at 2, 8. See if I can find 2, 8 right there. Thus, I'll find one over here at minus 2, 8 right there. So it's perfectly reflected through origin. And that's an odd function. And you might say, well, yeah, it's got an odd power. But that's not always true. You can find it with, yes, you'll find it with all the odd power ones, but you also find functions that are reflected through the origin that aren't just x to the 5 and x to the 7. And there's a mathematical way to discover if a function is perfectly reflected through origin. We'll get into that. And then you'll notice functions that are reflected in the y-axis. The right side is perfectly reflected on the left side through the y-axis. And yes, all the to the power of 4s follow that rule. All the even functions follow that rule. But there's some other functions that follow that rule as well. Let's see if I can, well, I mean, a horizontal line follows that rule. The left side is perfectly reflected in the right side through the y-axis. And so that's what an even function is. It's perfectly reflected through y-axis. And then you have what's called an odd function, I believe, which they don't, oh yeah, odd function, there it is. And then continuous function just means there's no break. But discontinuity means there is a break. And you have to learn how to spot that break. And here, a good one of that they use in this example is 1 over x. When it comes to x is equal to 0, it can't continue through. This whole line is independent on this side, and this whole line is independent on this side. And the discontinuity occurs when x is equal to 0. It can't exist. And that would be a break. But you can also have them in things like y is equal to x, and then you just say x cannot equal, and I forget the simple, let's see. Well, x is bigger than 3. So there's a good example. This line is a straight line until we hit there. And that's because x values don't exist at 3 and lower. So we can see at 3, we get the hollow circle, and it says undefined. And that's because I put a limitation on its domain. And so this is a discontinuous line. And you can add another one, for instance. And let's say x is smaller than 3. And this line, and I'll just make it the same color, looks like it's continuous, doesn't it? Until we click on 3 and we'll see undefined. And that's because this line I've essentially said x can't be equal to 3. So this is a discontinuous line, and you'll discover this in various things. And you also discover the definition of discontinuous because it's got more complications than I've just explained. Discontinuity. So those are things you have to learn in addition to what you had last year. And then notice they go through some summaries. The range goes on forever. Oh, they're saying match this. So y is bigger or equal to 0. And so we know it's not 2 to the x, but it is indeed the absolute value. Domain XER, well, that could be a lot of them. It could be the line. It can be the absolute value. It can be the growth curve. It can be the sine curve. It can be to the exponent, power curve, exponential curve rather, and sine. So they all have XER. Infinite number of zeros, which means it goes through the x-axis over and over again, which is the sine curve. And yeah, they're going through them here. And then as x approaches negative infinity, y approaches 0. So that means as you approach infinity on the left side of the graph for x, y approaches 0. So that would be the exponential curve here. Never touches x is equal to 0. And sure enough, they go through it here and there, right there. And then they explain it as well. And then they give you some word puzzles of how to figure it out, and like this. State which of the parent functions in this lesson has the following. So domain XER, but the range is YER, but it goes between -1 and 1. And I can tell you right away, that's going to be a sine or a cosine curve, and both. So since in this case they've only given you the sine, they might only be talking about the sine. So they go through them each. They go through the line. They go through the parabola. They go through 1 over x, and they say, okay, well, 1 over x doesn't have XER. And they rule them out one by one. And then they say, okay, well, this has a range that goes on, so it doesn't match, until they finally say the only one left is I don't know why they do this and then highlight the line. So they essentially come to the conclusion of these 5 functions, only the sine function has the range that we're looking for, even though they've accidentally crossed out the sine. They meant to cross out the line, I think. Visualizing the function, so which of the following characteristics, so they're describing it, and you have to explain the graph decreasing for all values in the domain of p of x. No, it's increasing. The graph is continuous. Yep. The function p of x is an even function. No, it's not reflected in the y-axis. The function has no zeros. I think by definition, when there's zeros, they don't mean the y-intercept. They only mean the x-intercept. So the graph is decreasing, so it goes through it. Yeah, that's true. The graph is continuous. That's true. It is not an even function. That's true. And it has no zeros. So only B and D are characteristics. Actually, oh, it says decreasing. Yeah, it's increasing. So A is not true. So only B and D are true for that. And they just want you to be able to visualize by words. I have to say that this section's the most useless. So this one is, it's transform parent function. So its domain goes on forever, but its range is bigger or equal to -2. So that could be a parabola whose vertex is at whatever, comma, -2. See, it's decreasing on the interval up to 0 and increasing on the interval from that. So again, it's can't be a parabola if it's facing down, though. Decreasing, increasing. I think they actually got this wrong, because for it to face up, it would have increasing and decreasing. Oh, bigger and equal to -2. So yeah, so it's an upward facing parabola. So yes, as they conclude, it's either a parabola or an absolute value graph. So it has a vertex. I don't like doing these questions because I don't believe there's a lot of value in interpreting the visuals, but I mean, I'll try. I'll go through it. I prefer actual mathematical functions. Which graphical characters is the least helpful for differentiating among the parent functions? Why? Probably the domain, and that's because many of them are XER. So because so many of them are XER, it doesn't really help to know that it's XER, whereas the ranges usually have more restrictions. Which graphical characters is the most helpful? And again, I would say possibly the range, because for instance, growth curve, range is y is equal to b is 0, y is bigger than 0. Parabola, the range is limited by the vertex y, and is y and upwards. Even the 1 over x curve, which looks roughly like that, y can't be equal to 0. So that means y is bigger or smaller than 0, but never equal to 0. So you can see that the range is pretty useful, I feel. Don't know if that's the answer they're looking for. One of the 7 pair functions examined in this lesson transformed to yield the following. The domain, you can see that doesn't tell us much. Y is bigger than 2. As x approaches negative infinity, y approaches 2. Interesting. So I'm going to suggest that that is a growth curve or a decay curve. Now I'm going to say it's a y is equal to 2 to the x plus 2. So that would raise the value of its asymptote from, which is normally at x, it would raise it up 2, which means y is always bigger than 2, it never touches 2, and that as x approaches infinity, y approaches 2. So you can see way over here on the left, it's trying to reach the 2 but never gets there. You can confirm that with Desmos. There's actually more answers than that, but I don't want to get it too confusing. Okay, now we'll do some of these. Okay, for each pair, actually we're going to just skip that and we're going to just read it. For each of these pair, give a characteristic that the two functions have in common and a characteristic that distinguishes them. So now they have restrictions on the XER. Their ranges have restrictions. So distinguishes them, XER in this one, and X can't is ER, but X can't be equal to 0 on this one. So that distinguishes them. What do they have in common? They both have intervals of increase at one point. Actually, no, this one only has intervals of decrease. So this one has only intervals of decrease, and this one has intervals of increase, so that's something that distinguishes them. In common, I don't think they have anything in common. This one's discontinuous, and this one's continuous, so another that distinguishes them. I don't think they have anything in common, actually. Okay, what about this? Okay, easy. They both have XER. Their domains go on forever. But this one has a range limitation. -1 is smaller or equal to y, which is smaller or equal to 1. And this one's range goes on forever. So this distinguishes them, and this is in common. Okay, so what about this? You can see how this is sort of useless, except in learning the domain and range of each. Easy enough, the same thing. The domains are the same, but the ranges are different. This one has a range that goes on forever, and this one's range is bigger or equal to 0. And finally, the last one. Fair enough. This growth curve looks like this. It never touches the x-axis. This absolute curve looks like this and has a vertex right here at 0, 0. So you might say their ranges are the same, but they aren't. This one's bigger or equal to 0, and this one's bigger than 0. So their ranges are not the same. However, their domains are the same. XER, XER. So again, you can say their domains are the same, but their ranges are slightly different. That's good enough, I think. This one has a interval of decrease and then increase, and this one just only increases. So there you go. You can see you don't really learn any math from that. You just learn sort of characteristics for each of the function. Calculate and compare. Okay, so here's how you figure out if the function is odd or even. Okay. Let's say you have this. So if I replace x with minus x, and I get the same equation when I'm done, it is even. And if I replace x with minus x, and I get close to the same equation except that there's a minus in front, it is odd. And you'll discover that that is the way to discover if a function is odd or even using algebra. So let's look at that. Let's look at this one. So we're trying to figure out if this is odd or even. Now, a couple things help you visualize it. I happen to know that this is a difference of 2 squares. Notice that it's a difference of 2 squares. I also notice it's a parabola. And that tells me it's a parabola that's going to go both through minus 2 and 2. And because that, it's also facing upwards, I know that it's going to be even. So right away I know it's going to be even because their x-intercepts are equal distance to the y, and a parabola that has equal distance to the y is going to be even. But to prove it, I'm going to replace this x in the middle here with minus x. So we're going to rewrite the entire equation, except in brackets, I'm going to put minus x squared minus 4. What's minus x squared? It's x squared minus 4. Is that the same equation as this? Yes, it is. Therefore, it's even when I replaced x with minus 1. When I replaced x with minus 1, I ended up with the same equation, which means it's even. Let's continue to test this theory. Okay. You'll need to have a better knowledge of your sine curve and minus x. And you might say, well, I don't know if the sine of minus x. Well, for this you'll have to use an example. Sine of 90 is 1. So sine of 90 is 1. But sine of minus 90, which is over here, is minus 1 plus x. So I believe we will have actually a reflection. This creates a reflection in the y-axis. But because sine curves start like this, it will only end up doing this. Oh, it accidentally created a... Yeah, but it still ends up being an even function. So let's try that out. So go to this. We'll do y is equal to sine of x, and we're going to do y is equal... And you're not going to see a difference, I don't think. Well, you might. Yeah, so that makes sense. That actually proves that it's odd, because I didn't get the same equation. I got an equation with a minus in it. And that makes sense because a sine curve you might think is an even equation, but it actually doesn't reflect the other side. If it did reflect even, if it was an even function, you would see the exact same thing here over on this side. You'd see it jump up like this. See, it would be reflected exactly in the y-axis, but it's not. It's reflected down there. Everything up here, I'll just focus on the up, is down there. So a sine curve is actually an odd function. So is a cosine curve. And possibly a tan curve as well. Let's see. Tan x. Yeah, so tan is not an even function. It's reflected through the origin. Over and over again. Let's just make sure by doing y is equal to tan minus x, it should jump. Yeah. So tan curve, cosine curve, they're all odd functions. And you come up with that when you say, oh, well, the only difference here now is there's a minus in there. And some of them resolve easier and some of them don't. Like that one takes a little logic to understand what's going on. Okay, let's put a minus where the x is here. And the only thing that happens is I get minus 1 over x minus x. So it's the same equation, except that I have a, oh, actually, yeah. So I have to put a minus with this x as well. So I get minus 1 over x plus x. And you can see it's the same equation, except all the signs in front have swapped, which is a sign that this is an odd equation. So let's see it in decimals. Y is equal to 1 over x minus x versus y is equal to minus 1 over x plus x. Yeah, so you can see that they totally inversed, and that means it's an odd equation. Even visually, without that, you can see that this left one is the same as this right one, reflected straight through origin. So that's a reflection of straight through origin when y is equal to minus x. So you can see everything that happens on the right side of the green line is mirrored in through the green line on the other side. They're always going to be, all the values here go down to here, and all the values here go over to here. And actually, the green line isn't an accurate representation because it's being reflected right through origin. If I use origin as the middle point, if I take a dot here and then go straight through origin, I'm going to find the equivalent dot on the other side. If I take a dot here and go straight through origin, I'm going to find an equivalent dot up here. If I take a dot way up here, 10, and go straight through origin, it's going to go down to 10 down here. And that's what an odd function is. It's reflecting through origin. And you discover it when you replace your x with minus, and you still get the same equation, but all the symbols change. If the equation comes out the exact same, then it's an even function. And you'll notice that whenever it's cubic, it's going to come out different. So I'm going to replace my x with a negative plus minus x. And when this gets cubed, it doesn't disappear. It stays the same. So now that becomes minus 2x cubed minus x. Notice I have pretty much the same equation, except the symbols in front reversed, which is a sign that this is indeed an odd function. I'll just use the main one, 2x cubed plus x. And sure enough, you can see that it's reflected perfectly through origin. Not so for this one. You can already see in the x squared that this will not be probably won't be an odd or an even. So if I replace x with minus x, and over here I replace x with minus x, this becomes x squared again. So that part stays the same, but this part changed. So notice that all the symbols didn't change, and it's not the same equation. Therefore, this will be neither odd, it won't be odd, and it won't be even. It won't reflect through either. Let's have a look. 2x squared minus x. Yeah, See that? That doesn't reflect through anything. If anything, its reflection line is over here at its vertex, which is 0.25. But it doesn't reflect through the y-axis, and it doesn't reflect through the origin. So that proved, because we came up with an equation where the symbols did not flip opposite perfectly, and it is not the same equation, that it's neither odd or even. Okay, we're going to go on to F. This one might be interesting. Okay, when I replace the x with minus, I get minus 2x plus 3. And then when I take the minus out of it, I get minus 1, 2x minus 3. This is interesting. If we go to the original, we're looking at something that is shifted to the left 3 over 2. And when we look at this one, we're looking at something that is shifted to the right 3 over 2. So right away I can say that it's probably not going to be even. And I don't think that counts as the yeah, okay. Let's go back and let's factor it correctly so that we can see what if the equation actually changes. So that's the correct translation. Now I'm going to replace x with minus 1. So I get 2 minus x plus 3 over 2. And I'm going to factor out the minus 1 from there. So I get minus 2x minus 3.5. So all my symbols did indeed change, and the equation's still the same. So I'm going to say that this is indeed a it's a big gamble here, because absolute functions tend not to do this. I'm going to say that it is indeed, it's saying that it's an odd function, but it really shouldn't be. Y is equal to absolute of 2x plus 1. No. So I guess because I didn't get the same thing at all, doesn't matter if that's 3 or not. Yeah, 2x plus 3. Yeah, so that is a good example of something that sort of betrayed me. I guess the minus would have had to come out front for it to actually be something. Yeah, it makes sense that there's no way that that could be reflected once you realize that it's a slightly offset absolute value. However, the equation made it seem like it was possible. So that's an interesting one. I think that any absolute value thing that's translated to the right or left obviously can't reflect into anything. So it just helps to know your graphs. But interesting that I was making a mathematical mistake there somewhere. You can see why I don't like these. Determine a possible parent graph for the following. Yeah, I hate these. These to me are useless. And explain your choice. The number of marks away from the class average that a student's test score is, that would be an absolute value. Much like that number line we use, the middle would be the class average, and all the marks away would be an absolute value. The height of a person above the ground during several rotations of a Ferris wheel, that would be a sine curve. All wheels follow a sine curve. The population of Earth throughout time, that would be a growth curve. As people have more babies, their babies have more babies. Now, if everybody just had one baby, the population of the Earth would, I believe, decrease because 2 people become 1. If everyone just had 2 babies, I'm not sure if this math works out, and those 2 babies had 2 babies, that's a good question. 2 people have 2 kids, and these people have 2 kids, and their kids get together and have 2 kids. I believe the Earth population would stay the same. But of course, people don't have 2 babies. They have 3, 4, 5 kids. So Earth growth is a growth curve. The amount of total money saved if you put aside exactly $1 every day. You'd think that's going to be a growth curve, but if there's no interest, it's not. It's just going to be a straight line. You know, each day represents another dollar. So after 4 days, you have $4. Identify a parent graph who has the following characteristics. The domain is not all real numbers, and f of 0 is equal to 0. Okay, that could be a function curve, like that, because the domain is restricted to there, and f of 0 is equal to 0. The graph has an infinite number of zeros. Okay, that would be a sine curve. The graph is even and has no sharp corners. Is even, so parabola. And as x gets negatively large, so does y. As x gets positively large, so does y. So that would be a straight line. Now, the question is, are they talking about one function here? I don't believe they are. The domain is xer. The interval increase is as x goes to negative infinity, y goes to positive infinity. And the range is bigger than -3. Well, that would be a parabola whose vertex is at -3, comma anything, or sorry, 0, let's say anything, comma -3. However, it says bigger than -3, not equal, so it's not a parabola. So I think it's a decay curve that's been lowered to -3. So right here, here's a decay curve. So as x goes to negative infinity, y goes to positive infinity. And if it's all been lowered by 3, it will never hit the line -3. So that means f of x is always bigger than -3. So I believe we're looking at a decay curve. That's been lowered by 3. And that matches that. The range of g of x is any real number such that this is such that it's limited to this. Well, that could be a sine curve who's been stretched and raised by 1. So this means it never goes below 2, but it equals 2. It never goes above 4, but equals 4. So here's a sine curve. If it goes up to 4 and down to 2, that's the same as a sine curve that has an amplitude of 1. Its axis is at 3. So that would be y is equal to sine x plus 3. If in doubt, go to Desmos. And there we go. We have something that never goes but equals 2 and never goes above 4. And you can see its axis is at y is equal to 3. And its domain is going on forever. And then the domain of this is such that x can't be -5 or 5, and the range is such that it can't be -3. Well, that's going to be a rational curve. 1 over, if it can't be 5, then we're going to have x minus 5 down here. And we can see that when x is 5, the whole thing's 0, so that means it can't exist. So x can't be 5. And to create a domain where, a range where it can't be equal to -3, you have two choices. You can either lower the whole thing down to 3, like that, or you can create a x minus 5 up here and put a -3 in front, or even just a -3x. You don't need that 5. Let's try both things. -3x up top will work. That'll create a horizontal asymptote at -3, or lowering the whole thing by 3. One over x plus 5, or x minus 5, and then minus 3. Go home. There we go. So let's see if our horizontal asymptote is at minus 3. It is. And let's see if we got our vertical asymptote at 5, and we did. And we'll make it blue. There we go. We did it. Let's see if the other system would have worked as well. And how I did that is realizing how to create a vertical asymptote down here was to shift the whole thing to the right by 5. And to create a horizontal asymptote that's no longer at 0 is to shift the whole thing down by 3. This would also work. And there, I've achieved it there as well. We'll get more into what's happening here. And that's creating a different type of horizontal asymptote. And that's when the power up here is the same as the power down here. The horizontal asymptote is dictated by the ratio of the coefficients in front. So minus 3 over 1. But I could have also put a 2 up here and put a minus 6 up here. What's minus 6 divided by 2? Minus 3. Creates the same horizontal asymptote. So you're going to learn when the powers of x are the same, the horizontal asymptote is dictated by the coefficients divided. I could also do it with minus 12 over 4. See? Minus 12 divided by 4 is minus 3. We'll get more into that. Okay. Sketch a possible graph for the next two functions. And I don't know if I'm going to do these, but we'll try. And I don't like them because it's just kind of pointless. Okay, so f of 0 is at minus 0.5. f of 1 is equal to 2. Oh, geez, there's a vertical asymptote. As x gets positively large, y gets positively large. As x gets negatively large, y approaches 0. This looks like, oh, how can you have a vertical asymptote, though? Oh, this is a I believe is a rational function again. So we can't be at x minus 1. And to create that, we do x plus 1. So that when x is minus 1, this thing at the bottom is 0. So that's solved. This will be true for that, and this will be true for that. But will we get that? So when x is 0, we got 1 at the bottom, so we need negative 1.5 up here. Either that or we need a negative down at the bottom. Negative 1.5, but that will inverse our thing. That'll turn our thing upside down, which won't get us this. And when f is 1, yeah, that doesn't work. So this is not right. So let's just keep this. But let's do it when f is 0, we get negative 0.5. But if I lower it, I'm no longer going to be approaching 0. Well, that's a tough one. Well, let's see what we can do on the graph instead. So we're going to start with 1 over x plus 1. So that's going to create our vertical asymptote. But notice that it's approaching 0. It's supposed to be approaching infinity. So I definitely don't think this is right. Let's look at 1 over x squared for a second. No, we need something that's going way up here as y is going way up here. So it's not a reciprocal. What else has vertical asymptotes? Tangent. But tangent doesn't meet these conditions. So you can always go look at your parent graphs to see if one matches what we're looking for. No, none of those will. That won't. I mean, that does. So growth curve does. So growth curves don't have asymptotes. It's a good question. The only way to create a vertical asymptote is if the bottom has this. And if it's just this, when x is 0, we get 1. So it's not that. And it also doesn't meet these two conditions. Yeah, that's a good question. I'd have to look at the back of the book for that one. So we got a quadratic function. Notice the t here, so I'm probably not going to answer it. The graph of fx decreases on the interval here, which means from minus infinity to minus 2. So as it approaches minus 2, from minus infinity, the graph decreases. It's going down. It's a quadratic function, and it increases from 2 to infinity. It has a y-intercept at 0, 4, so crosses the y-intercept at 0, 4. Probably not. Probably more than 1. And probably yes for that. Jeez. I wouldn't bother with this one, but I mean, you could do a x minus 4 x minus 2 x plus 4 x plus 2. And let's just make them close together. Okay. Well, it looks like I accidentally nailed it. Except that I'd have to raise the whole thing. I think if you do x minus 2 twice and x plus 2 twice, you get what you want. Just that's too high. But it still works now if I lower the whole thing by 12. So now I get 0, 4. My thing is decreasing from negative infinity to negative 2. It's increasing from 2 to negative 12. And I'm at 0, 4. You can also have that with a to the power 6. Okay, and then the only thing you'd have to do now is you'd have to instead of decreasing that, you'd have to raise it by like 80. Almost. 78. This just takes familiar. Oh, didn't hit it at all that time. I think I got it there, 68. Yeah, there we go. And then I have an interval of decrease. That's, well, it's a slight problem. It doesn't quite work like that. So I think I have to have a couple X's in here instead. And then just stick to my original. And just raise it by 4. So there, I've hit my criteria with this one as well. And this one's to the power of 6. So there's several functions for that one. Again, that's come from fiddling a lot, understanding your quadratics. One has a sharp corner. This one has a sharp corner. And that's going to be really important in calculus. So this one has all smooth lines. Yeah, so this one has all smooth lines. This one has all straight lines. This one has a rounded corner. This one has a sharp corner. And other than that, I'd say they're very similar. This one was really tough. I'd like to look up the answer to that one. Anyway, you can see why this chapter gives me problems, because it's a lot of visualization. Copy and complete the following table. That's just so you can learn your graphs. I strongly suggest you use Desmos, but also understand what end behavior is, which means on the far right of the graph, where does the y values end up as x approaches positive infinity, and as x approaches y negative infinity. Figure out if there's any symmetry, figure out the standard y-intercepts, figure out the zeros, that would be x-intercepts, figure out if there's asymptotes or discontinuous, intervals of increase, intervals of decrease, range and domain, and you want to be able to sketch. So you can see it's important that they definitely want you to know these basic parent functions. Linear, quadratic, reciprocal, absolute value are examples of different types of functions. Why do you think it's useful to name these types of functions? Okay, so in science, nature behaves a lot like these. That's why they're teaching them. So, for instance, quadratics behave a lot like gravity. Reciprocals behave a lot like, what would be a good example of reciprocal? Oh, I can't think of it, but there are things in nature that we'd want to use. Absolute value, you can see we use it in blood pressure, square root. What was it? I used to know examples of it, but essentially in science, these all have a function. In studying things that occur in finances, nature, light, physics, biology. Biology has both growth curves and decay curves. Consider the parent function x cubed. Graph f of x and compare and contrast this function with the parent functions you have learned about in this lesson. So that's just asking you to study cubic, and it's very important actually. Explain why it's not necessary to have f of x equal to cos f defined as a parent function. Maybe because it's simply sine x that is phase shifted 90 degrees. Suppose that g of x is equal to absolute value of x is translated around the coordinate plane. How many zeros can the graph have? Discuss all possibilities and give an example of each. Translated. Up, down, left, and right. Well, it can only ever have 2 zeros, 1 0, or 0 zeros. And that's because of this. The same as a parabola. If you look at the original absolute value of x, you will notice it touches right here. So that's 1. If If I raise it by 2, it never touches the x-axis, so it has no zeros. If I lower it by 2, it now crosses the x-axis in 2 spots and has 2 zeros. But no matter how much I lower it, it will only ever have 2 zeros. And no matter how much I raise it, it will only have 0 zeros. So just like a parabola, it can have 0 zeros, 1 zero, or 2 zeros, and that's it. Same with a parabola. That's why finding the roots of a parabola is handy. See, it can only ever cross in 2 spots, 1 spot, or 0 spots. Here's the 1 spot. That's when its vertex touches the x-axis. That's how you know. And that's why learning the quadratic function, especially this part of it, I think it's b squared minus 4ac. Okay, this part, when this comes out negative, that means the parabola does not cross the x-axis. It's above or below. When this comes out to 0, there's only one solution, which means the parabola is touching the x-axis. And when this comes out as a positive number, it means the parabola crosses the x-axis in 2 spots. Okay, so that's how you learn it. This is called the discriminant, and the discriminant can save you a lot of time. And there you go. Not a very useful chapter, and I didn't explain it too well, but essentially learn your parent graphs very, 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 very well.